Welcome to the end of cycle 8. So today we're going to do what we typically do. We're going to look at all the different propositions in this particular cycle, starting with proposition 16. So I have the enunciation here on the screen already, and it says, in any triangle, if one of the sides be produced, the exterior angle is greater than either of the interior and opposite angles. So we begin by drawing a triangle ABC, and we're going to produce BC in a line to D. And we'll choose some point D over there. So at this point, Euclid tells us what he's after. He says, I say that the exterior angle ACD, so this angle there, so the exterior angle ACD is greater than either of the interior and opposite angles, CBA, which is this one, and BAC, which is this one. So the exterior angle at C is greater than either the angle at A or the angle at B. That's the claim. So our next step then is to bisect AC. So Euclid says, let AC be bisected at E. And then the editors have given us here in our book that this is proposition 10. And one of the questions I asked was, why do we use proposition 10 here instead of proposition 9? And the answer is pretty simple. It's that proposition 10 bisects a line, whereas proposition 9 bisects an angle. And it's easy to make this mistake and to think that if we bisect this angle, the angle at B, that AC will also be bisected, but that's not necessarily true. So we have to be very careful to use the correct proposition. So I'm going to bisect AC using proposition 10, and of course we'll do this by beginning with some circles. As always, draw in our equilateral triangle like so, and I can now do proposition 9 either by joining these 2 points, or what I can do is I can actually draw proposition 9 up here, which is what I'm going to do just to make it more interesting for myself. So I'll choose some point at random there, and I'll use that to draw my circle and to select the point on the other side of my equilateral triangle, of course. And now to complete the equilateral triangle, draw these 2 circles. And of course now this gives me my second equilateral triangle, which is going to be there. So there's my equilateral triangle there for proposition 9. Then I just have to follow these 2 lines down to see where they cross at that point there. So now I'll draw out a ray like so. And you'll see, by the way, that this does not actually pass through point B, which is why it looks like if we were to bisect B, it may actually bisect AC, but it doesn't. It barely misses. And this, of course, gives me my point there of bisection. So that's going to be point E. And we're going to now produce a line from BE all the way to F. And I'll do this by drawing another ray like so from B to E. You'll again notice that my bisecting line here does not coincide with this other line that I just drew. This is why we have to be very, very careful. So I've drawn my ray from BE, and now I have to find a point F, which is equal to BE. How do we do that? By drawing a circle, of course. So I'll take my center point as E, and I'll draw this out to B. Now I have a circle there, and we have to, again, be very careful to connect the correct circles. You see that these 2 circles are very close together, but we have to choose the correct point. And because I have the ability to zoom in, I'm going to go ahead and do that, and I'll select the right point. So now I have carefully zoomed in, and the circle that I drew was the green circle, which maybe you can tell that that's green, but I have to make sure that my point lies there and not on the gray circle. So that then is my point. So I'm going to zoom out, and then we will carry on. Okay, so now I have my point up there, which I'm going to label F. So there is F. So the next step we have is to join F and C. So I'll do that now. We join F and C, and our figure is complete. And I'll trace around the figure as well to help you distinguish it from all the other things that we've done in our intermediate steps. So there we have our figure for proposition 16. Let's walk through the argument. So he begins by saying, since AE is equal to EC, AE is equal to EC. We know that these two lines are equal, of course, because we bisected AC at point E. Therefore, of course, each side is equal to the other. And because we have also drawn EF equal to EB, that means that these two sides are equal to each other as well. Which means, of course, that AEEB is going to be equal to CEEF. And because of proposition 15, we know that the vertical angles there are equal. So now we can apply proposition 4, because we have a side, an angle, and a side equal to a side, an angle, and a side. Which means that the whole triangle EBA is equal to the whole triangle CEF. So these two triangles are equal to each other. And of course, this also means that the other angles are also equal to each other. Namely, this angle there, the angle at A, is going to be equal to the angle at C. Those two angles are going to be equal because they're the corresponding angles in equal triangles. And we can also say, which I'll just do just for the sake of illustration, the angle there is equal to the angle here at F as well for the same reason, right? Because they're just corresponding angles in equal triangles. But the interesting thing that we've proven at this point is because the angle here at A is equal to the angle at C, this means that the whole angle ACD, right, this whole angle ACD is larger than the angle at A. So we've proven one of the things that we set out to prove originally, that in any triangle, if one of the sides be produced, that's going to be BC produced to D, the exterior angle, that's ACD, is greater than either of the interior and opposite angles, which means that ACD is greater than the interior and opposite angle A. Now we can also prove that this angle ACD is greater than the angle, the whole angle here at B, ABC. And Euclid doesn't do this, he just says that we could prove it. And I'll show you how we would do that very quickly as an example. So to show you how Euclid would go about proving that the angle at B is also smaller than the angle ACD, I'll walk you through a quick version of that proof. So what we would do is we would now draw line AC and extend that out to some point, because now this is going to be the base, or take the place of the base, and do the job that BD is currently doing in this figure. So you have to imagine that we are rotating this figure like so. So at this point, what we would have to recognize is because we have drawn this line, this red line down there, this ray, we have vertical angles. So the angle that we're interested in, our given angle, the one that we started with, ACD, our exterior angle, is equal to this exterior angle as well. So now all we have to do is reconstruct the figure just like we did here, but now on base AC, whatever other point this would be down there. So to do that, we have to bisect this side, BC, just like we did before, which I'm not going to walk through that actual bisection. I'll just choose a point, and we'll just assume that that's the bisecting point. And then I'll shoot a ray off, like so. And now what we do, and again, I'm just sketching it out. I'm not going to actually walk through all these steps in detail. I just want you to get a sense of how it would be done. So if we have this bisection here, then we have to choose some point over here, which is going to be equal to this length here, from A to this point, and then we'll choose a point equal in length over here, which we can, well, we'll actually do that. We'll use a circle for that, just to show you. So we'll choose a point, and the point's actually going to be down there, which is a little bit off the screen. So we would choose a point like so, and now our figure would be done. And so, because of the relationships we've already established, we know then that we have two triangles which are equal. We have this angle is equal to this angle because of proposition 15. We know that this side is equal to this side because we drew them the same length. And we know that this side here is equal to this side because we bisected BC at this point there. So we have a side equal to a side, an angle equal to an angle, and a side equal to a side. So we can apply proposition 4 again and say that these triangles are equal to each other. But if that's true, then that means that all the corresponding angles are equal, and that means that the angle at B is going to be equal to the angle which I'll label in black now, this angle here, right? So the angle at B is going to be equal to the angle, the black angle there, which is only part of this other angle, which is equal, of course, to the exterior angle. So again, we've proven that the angle at B is still smaller than the exterior angle. And it's really exactly the same reasoning, simply applied to a different side, that allows us to say with certainty that it doesn't matter which angle we look at, whether it's the angle at A or the angle at B, they are both going to be smaller than this exterior angle at C. Now let's quickly go through propositions 17, 18, 19, and 20. So proposition 17, I'm not even going to bother writing the enunciation out because you can look at it in your book, but it says in any triangle, two angles taken together in any manner are less than two right angles. So this, of course, is building on proposition 16. So we've got a triangle, which I'll draw something like the one in your book, and we can label these points accordingly as well. And so the claim then is that if we have a triangle ABC, that any two angles taken together, it doesn't matter whether we choose A plus B, or C and A, or B and C, that any two angles are going to be less than two right angles. And the way that we prove this is we extend BC to point D, and we apply what we've learned from proposition 16. So we know from proposition 16 that the exterior angle here is going to be greater than either of the interior and opposite angles. So the angle at C is going to be greater than the angle at B, for instance. And then what we're going to do is we're going to add this angle here at C, so the angle BCA or ACB. And if we think about this, and we can add the green angle plus the red angle, we can do the same thing here. We can add the blue angle and the red angle. So we have green plus red and blue plus red. We know that because the green angle is larger, that the blue and the red angle together are going to be less than the green plus the red angle. But because it's lying on a straight line, line BD, the green and the red angle together are equal to two right angles because of proposition 13. Which means that because the blue and the red angle together are less than the red and the green angle, because of course the blue angle is smaller than the green angle, this means that the red plus the blue angle must be less than two right angles. And we can apply the same reasoning again by sort of redrawing the figure to account for angle A, which we're not going to do because Euclid doesn't do it either. But I hope that you can see at least how that would be done. We would just extend this line, BA, out to some point here, and then just redraw all this, and we would say, okay, well, the exterior angle is greater than the blue angle. We add that little other angle there at A to each one, and we still find that this arrangement here is equal to two right angles, but when we add the red plus the blue, it's less than two right angles. It has to be, because the green is always going to be greater than the blue angle by proposition 16. So this now brings us to proposition 18, and we again begin with a triangle. And I'll draw it something like the triangle in your book, but it doesn't have to be drawn that way necessarily. We'll just do it this way just to make it easy. So we have triangle ABC, and the claim here is that in any triangle, the greater side subtends the greater angle. Now we've drawn this to make it clear which side is the greater side. AC is obviously greater than either of the other sides. And so the claim is that because AC is the greater side, that it's going to subtend the greater angle. That is to say that the angle at B, which of course subtends this side, is going to be the greater angle compared to A and C. So Euclid says, for since AC, that's our long side here, is greater than AB, so we're going to compare the long side to the shortest side because it's often useful to compare the extremes just to make things very, very clear for ourselves. He continues, let AD be made equal to AB. And this again is going to be where we're going to use proposition 3. So the way that we choose point D equal to AB, of course, is by simply drawing a circle, which I will do like so. So now we have point D. And of course, let BD be joined. So there we have that now. So we have A, B, C, and also point D, and we've joined D, B. So now we get to the argument. He says, then since the angle ADB is an exterior angle, so ADB is an exterior angle, because now we're considering this as two different triangles, or really we've got one triangle DBC, and we're considering this angle ADB, the exterior angle of this triangle DCB. And because it's the exterior angle of triangle BCD, it is greater than either of the interior and opposite angles. That is to say, it's going to be greater than this angle at B, and it's going to be greater than this angle at C. So the black angle is going to be greater than the green or the blue angles. It has to be, right, by proposition 16. But we know that the angle here, the black angle there, is equal to the angle right here. Why? Because this is an isosceles triangle. This side's equal to this side. And by the propositions we've had on the isosceles triangle, in particular proposition 5, we know that the angles at the base have to be equal. So the right angle is equal to the black angle. But now look at what we have. We have these two angles paired together. So we know that the black angle is greater, of course, than the green or the blue angle, but in particular we're interested in this blue angle here at C. That's the angle that we're interested in. So the black angle is clearly larger than this blue angle by proposition 16, but if we then add the black angle, which is larger than it, to this green angle, it doesn't really matter what the green angle is because the black angle is already larger, then this means that this angle at B is much larger than this angle at C. And so what we find is that the shortest side subtends a smaller angle than the largest side, which subtends a clearly much larger angle. Here we have proposition 19. Now proposition 19, of course, is the converse of proposition 18. And what we say for this one, we begin with our triangle ABC and the claim that in any triangle the greater angle is subtended by the greater side. That's the enunciation. And so we begin by giving ourselves an angle which we know to be greater. So the angle here at B is the greater angle. And this angle in particular is going to be greater than the angle BCA. So there's our other angle. So our large angle at B and the small angle there at C. And that's what we are beginning with. We're beginning with the knowledge that the green angle is larger than the red angle. That's our starting point. So then he goes on to say that therefore the angle or the side AC must also be greater than the side BA. Now, we have to prove this because proposition 18 goes from sides to angles, and now we're trying to go from angles to sides. So he says, okay, we want to say that side AC is greater than side BA because it subtends the smaller angle, but how do we know for sure? Well, we have to use a reductio proof. So if it's not larger, if AC is not larger than BA, it's either going to be equal to it or it's going to be smaller than it. So if then AC is equal to AB, this means, of course, by proposition 5, this would be an isosceles triangle, and the angles at the base, the angle at B and the angle at C, would have to be equal. But they're not. Why not? Because we began with the knowledge that the angle at B is greater than the angle at C. So that contradicts that, right? So we know then that AB is not equal to AC because that contradicts the givens. Okay, so maybe then AC is not equal to BA. Maybe AC is actually smaller than AB. But if that were the case, then AC would subtend the smaller angle by proposition 18. But it doesn't because it subtends the larger angle. Therefore, we can conclude that no other solution is possible except to say that the larger angle is subtended by the greater side and the smaller angle is subtended by the smaller side. All right, let's move now to proposition 20. And so the enunciation for proposition 20, of course, is in any triangle, two sides taken together in any manner are greater than the remaining one, which means that the angle, or the side rather, BA plus side AC is greater than side BC, or AC plus BC is greater than BA, or BC plus AB is going to be greater than AC. So any two sides, doesn't matter which order we take them in, but any two are going to be greater than the remaining side. And to prove this, we have to construct now a side, BA, and extend it, and we're going to do this to make an isosceles triangle out of it. So to do this, I'm going to also draw a circle there, and we'll choose this point here. Now the reason for this, of course, is I want side AD to be equal to side AC. And I join CD. So here now is our completed figure. So to proceed to the argument, because we know that side AD is equal to side AC because we drew them that way, that's what the circle was for, we know that because these sides are equal, the angles here are going to be equal as well. So know that the angle at D is equal to this angle there at C, because this is an isosceles triangle. But that means, of course, that the whole angle at C, is going to be greater, of course, than the black angle, which is only a part of it. So this means that the red angle at C is greater than the black angle there at D. That should be pretty obvious. But by proposition 19, that also means that the greater angle subtends the greater side. So because this is a smaller angle, the side subtending it, that is side BC, is going to be smaller than the side subtending the larger angle, which is side DB. So side DB then is larger than side BC. However, side BD is equal to sides BA plus side AC. Why? Because AC is equal to AD. So side BD is equal to the other two sides, and so what we've proven then is that these two sides, BA and AC, are greater, taken together, are greater than side BC. And we can repeat this argument for any of the other sides of the triangle, and again show that it doesn't matter which two sides we choose, they will always be greater than the remaining side. So this brings us next to proposition 21. And the enunciation for proposition 21 says if on one of the sides of a triangle from its extremities, in which in this case is going to be BC, that's the one side, there be constructed two straight lines meeting within the triangle, that is BD and DC. The straight line so constructed will be less than the remaining two sides of the triangle, but will contain a greater angle. That is to say, that if we have base BC and we have triangle ABC, and we just construct inside of triangle ABC a smaller triangle with sides BD and CD, because this is a smaller triangle fitting inside the larger triangle, side AB will be larger than DB, and as well AC will be larger than CD. DC and BD will be smaller than the original sides of the triangle. But even though the sides will be smaller, the angle contained there, so the angle there at D, will be larger than the angle at A. So that's what Euclid is claiming, and let's see how he goes about proving it. So to begin, we have to refer to proposition 20. And we do this by taking a look at triangle BAE. So this triangle right here. And because of proposition 20, we know that any two sides of a triangle taken together will be larger than the remaining side, which means that if I take this side here, which I'm labeling green, that side plus this side here, that's going to be larger than the other side, which I will label in red. So side EB is going to be shorter than the other two sides put together. That should be pretty obvious. And now if we add to this, if we add the remaining side, EC, so if you can imagine adding the two green sides plus the blue side, that's going to be larger than the red line plus the blue line, right? Because of course the green line's larger than the red line. So that's that. So if we take this and then we apply same reasoning to another triangle, which is to say we take this and we apply this to DEC, that triangle, we know that this bit here, which is DE plus the blue length, is going to be larger than DB, or sorry, DC rather. So DE plus EC is going to be larger than CD for the same reason, because of proposition 20. So if we add then length DB to both, so if we have this light blue bit plus this bit here, DB, that's going to be less than the whole length EB plus the blue bit, again because of proposition 20. So if we put all this together into a single thought, what we end up saying is that therefore lines A or BA, AC, we've just proven that that whole piece here, BA, AC, is greater than the two sides BD, DC because, again, of proposition 20. So we keep proving, for instance, that each piece of the original triangle is larger than the sides that make up the smaller triangle, right? This bit's larger than this bit there is larger than this bit, and therefore BD and DC are going to be smaller than BA and AC. So that's the first part of the proposition. The second part, however, is to go back and look at the angles. Because remember, we want to prove that the angle here at D is larger than the angle at A. That's what we want to prove. So how do we go about proving this? Well, if we start with the angle D, we can make some interesting observations. We know that the angle D here, the red angle there, is the exterior angle of triangle DEC, which means it's going to be greater than either of the interior and opposite angles by proposition 16. Which means, of course, not only is it going to be greater than this angle here at C, which is kind of obvious, but also it's going to be greater than the angle at E. So the red angle is greater than the green angle by proposition 16. But by the same reasoning, this green angle is the exterior angle to triangle ABE. And because this is the exterior angle, it's going to be greater than either of the interior and opposite angles. So not only is it greater than this little angle here at B, but it's also going to be greater than the angle at A. So by proposition 16, we can say the red angle is greater than the green angle, and the green angle is greater than the black angle, which means, of course, the red angle is much greater than the black angle. And that's really all there is to proposition 21. The next two propositions, of course, are propositions 22 and 23. Now, rather than walk through the proof, because both of these are constructions, my main concern right now is to make sure that you're able to do these constructions easily and correctly. And so to begin with proposition 22, we need to lay out 3 lines. And of course, these lines have to be such that any of the 2 lines are going to be greater than the remaining third line, which means I can't make my third line this long, because if we add these two, I think it's pretty obvious that it's shorter than this line, and so we're not going to get a triangle, we're just going to get a line. So instead, I'm going to make my third line this long. So there are my 3 lines, and now out of these 3 lines, we're going to construct a triangle. And I'll do this a couple times, just because it is very important for you to understand how to do this in a number of different circumstances, especially for proposition 23, which can be confusing if you don't understand how to apply these ideas. So I'm just going to draw a ray like so, shooting off through there. And so what I've just done is I've copied this line, which means that the radius of this circle is now this line. So I've made this my base. I didn't have to make this the base of the triangle, but I chose to. Next, I'm going to copy this line like so, and this is what you'd use with your compass and ruler. And again, you don't have to go through all the steps of applying proposition 3, because that's, I mean, you can if you would like to, but it's very difficult to apply proposition 3 to these, although go ahead if you think that that would be interesting. And so you're allowed in this case to pick up your compass, basically what I'm doing here, measuring out the circle and picking up your compass and placing it wherever you need it to go. So there are a couple different ways to do this. I could place this with center there, or I can place it with center here. And it doesn't really matter, it just changes the orientation of the triangle. I'm going to place it here though for now. And this means that we have one more circle to copy. And the question at this point is, where do we place this circle? Obviously, we can't place it in the center because now there are no intersections of the circles and we don't have anything. We just have 3 segments that don't connect in any way. So then the question is, do we place it here or do we place the circle here? Well, the answer is we can't place it there, because if we place the circle here, we've actually remade the base to be equal to this middle line there, because we've selected this as our base rather than this original base that we had, which was the first line. So I'm going to place this with the center there. Now when I do that, we next have to be very careful to connect the proper lines. So our base then is this length, and now the question is, where do we connect the lines? Well, we know then that the third line is accounted for because that's the base. So this outer circle is accounted for because that has given us the base. That's that first line there. And we know that this other line here, the second one, can be accounted for by being placed on this circumference. And the only place where it makes sense to join them would be here, or if we were drawing the triangle on the other side, perhaps there. But there is where we're going to put that. That means that the other line is going to go from here, and it's going to fall on this radius. The only place where that makes sense, again, is right there. That is the triangle constructed out of these 3 lines. That's how we go about doing that. Let's do a few more of these in different arrangements. And you can follow along, of course, and I hope that you've already done all this several times in your journal, like I asked you to in the guidebook. But because sometimes it's helpful to watch someone else work them out, I'll do a few more, and then we'll move on to Proposition 23. So next we're going to have some other sets of lines. I'll just choose these, again, more or less at random. And we're going to, we'll do this differently. We'll actually start with the short line as the base. So last time we did the long side as the base. We'll do the short side as the base now. And I'll just construct a line like this. So this is now going to be the base of our triangle, okay? So next I'll copy this first side, and then the question is, where do we place this? We really have a couple different options. We could place it here, or we could place it here. And it doesn't really matter. We just have to remember that whichever place we place it, the other side is going to have to join it at the other point. So I'll put this one for now at the center. And remember, this is the first line. So these two correspond. I should probably color code those. Let me do that. So we now know that this segment corresponds to the red circle because it's the radius of that circle. And then we have this last segment here, which I'll do in a different color as well. And so now to copy this side, we can't place it here again because then we don't have any intersections, and we don't want to place it here because that would give us the wrong base. So we need instead to place it here on our original base. And then of course we simply draw in the radii. So from this point, which is the center of the green circle, I follow the circumference down until it touches the red circle. We don't want to go to the black circle because the black circle has already been accounted for by the base. So we place it there. And now we go to the red circle and we follow that circumference, of course, to the same point. And now we have these 3 lines all accounted for, and we have our triangle, which, by the way, if you're having trouble copying triangles, color coding or labeling the sides and the circles in this way can be very helpful, because then you can see exactly where these sides fall and the circles to which they correspond. That can be a very helpful thing to do. Let's do one more and then we'll move on to 23. So here we have a line segment already, and this time I'm going to give myself some more lines, and we'll make them fall like this. And I'll choose again, you know what, I'm actually going to choose the center one here for my base. The center one's going to be the base. I'll place it there. So there's the base. Next, I'm going to choose the long side just because, and I'll place it there at the center. And then the short side I'll place last. Now the question is, where does this one go? I can't place it here because that would give me the long side as the base instead. And I want the middle side of the base, so it has to go with the center there to give me the middle side, corresponding, of course, to this circle and the radius there. So now, when we join the sides, we have to be careful again. We can't put the side there because that, again, would give us this side equal to the base, which is not what we want. And so we need to account for the long side by joining to the large circle, and then from this point, which of course also falls on the small circle circumference, we can put in the short side. And that's how to do that. So in Proposition 23, we have a very straightforward application of Proposition 22, because we know that we can copy any three lines into a triangle, which means, of course, that if we already have a triangle, it's very easy to copy. We just copy each of the lines, and we can reproduce the triangle. Now, we can use this, as we do in Proposition 23, to copy angles, because what are angles except triangles, essentially, without 1/3 side. So to make this a triangle, all I have to do is choose any 2 points to join, or I could even choose these 2 points, which I'll do just to make it easy on myself, and I'll redraw these to make it clear which side was the original angle. So there's our original angle, and I've simply joined this point there, and now we can copy this over using Proposition 22. So the way to do this is we simply choose a side to copy first, and I will copy the base. So I've got the base here, and I'll just place that like so. And now that I've done that, I'll put in a side. There we go. So there's my side corresponding to this base. Now, what I can do is I can copy a different side. Let's actually copy this side here because it's really clear to me where I need to place this circle. I need to place it at the edge of the base. If this is the base, that means I simply place it there, at that edge of the base. So now we've got this side copied. And I can't join these points, by the way, because that's not going to, even though this would be the proper length of this side, it's not the proper angle, because remember, that would require me to draw a line from there to there, which would give me 2 lines of equal length, but this is not an isosceles triangle. So we have to be careful. So to copy the last side here, this one should be pretty clear where it needs to go as well. It needs to be centered here at this side of the base, which of course is this point there. So now we can join our sides. We have a side from there to there that accounts for the side that we just copied. Then we have a side from there to there, which accounts for this side there. And we've copied this triangle. But in copying the triangle, we have also copied the angle, because all we have to do is extend these sides out and we produce an angle equal to the original angle. And this is, of course, an extremely useful thing to do and something that we'll be doing over and over and over again, so it's important that you're able to do this easily. We're going to do one more by way of example, and I'm going to copy an obtuse angle. This was an acute angle because it's smaller than a right angle, but I'm going to now copy an obtuse angle. So to redraw my angle here, we'll make it an obtuse angle. There's my obtuse angle. So how do we copy this? Well, we do the same thing that we did before, which is we join these 2 points to make a triangle, or we could have chosen any other 2 points, but I'm choosing these because that's most convenient for me at the moment. And then we select one side to be the base. I'm going to select this side to be the base, and I'll even bold it a little bit so you can see this is going to be my base there. So we make a circle with this radius, and we place it wherever we want it to go. And I'll draw in my side like so. There's my base. Next, we need a circle, another circle, and I'll copy this side here. Where does the circle go? Well, obviously it goes on one side of the base, there. And so I'm going to have a line extending from there. And then lastly, I need to have this side copied, which I'll do in a dashed circle as well. So a much larger circle at this time, but where does it go? Well, it has to go on the other side of the base because that's where it meets. So I'll place it there. And then the point at which the dashed circle meets this other thin circle is the point where my lines need to also correspond. So that means I can draw a line from here to here, because that's where those 2 circles meet. And then I can draw my other side in like so. And you see that not only have we copied the triangle, but by copying the triangle, we have also copied the angle. Now, as I have said before, there's more than one correct way to solve problem D. But what we're going to do now is we're going to look at one way to solve problem D. And what I have here is I've actually drawn out problem D for us. Now, I have intentionally drawn it out incorrectly because I want you to have to think through the logic rather than trusting your eyes. So let's see how I've gone about creating a proof that proves this enunciation here, which is what we were trying to prove. So we begin with ABCD as a square. So this is a square, even though I've drawn it so that it doesn't look like a square. This is a square. Can't trust your eyes. And let AC and BD be joined. So I've drawn in the perpendiculars. Let's see how the argument goes. So sides AB, that's this side, and BC and CD and DA are all equal because ABCD is a square, and this goes back to definition 22, right? Because we know that part of the definition of a square is that the sides are all equal. So we begin by establishing all the things that we know. We know that the sides are all equal, so I'll actually mark that for us to make it easier to visualize. All those sides are equal. And the angles ABC, BCD, CDA, and DAC are equal since all are right angles. And again, this just goes back to the definition of a square. So this is a right angle, this is a right angle, this is a right angle, and this is a right angle. And because they're all right angles, all those angles in the corner are equal. Therefore, triangles ACB and ACD are equal. So the triangles A, B, C, so this triangle here is equal to the triangle on the other side, ADC. So I've sort of divided this into two triangles. One triangle lies here, the other triangle lies here. Okay, so now we've divided it into two triangles. And the reason that we know these are equal is because of proposition 4 again, right? Because we know that this angle is equal to this angle and that the sides about them are also equal. Hence, the whole triangle is equal to the whole triangle. And then furthermore, because the angles DAC, so this angle here, the angle DAC, and BAC are equal. How do we know that they're equal? Because the triangles are equal, right? Therefore, we know that line AC bisects the angle BAD. So we know that this right angle at A is bisected by line AC. How do we know this? Because the angles on either side are equal, and we know that those angles are equal because the whole triangle is equal to the whole triangle. And then here I take a shortcut from in the style of Euclid, and I say similarly it can be shown that AC bisects angle DCB, which is the angle on the other side here, right? We can by the same argument. And also we can make the same argument by simply choosing two other triangles, which would be this triangle and then the triangle on the opposite side here. We can show that those two triangles are equal by the same reasoning, and therefore that BD also bisects this angle and that angle. Thus, we move on. Thus, because each corner has been bisected by the diagonals, because we've proven that the diagonals bisect each corner, the triangles DEA, so that's going to be each of these little triangles here. DEA, there's one triangle. AEB, there's the other triangle. BEC, there's the other one. And CED are equal isosceles triangles. So now we divide this into 4 triangles, and we find that they're all equal triangles. And then I explain how we know that they're equal triangles. I say, for instance, DEA, which is this one, DEA is half of triangle ACD, right? So it's half of this whole triangle there. How do we know this? Because we know that this angle has been bisected, right? And that this is an isosceles triangle because this angle is equal to this angle because both of these corners have been bisected. So because both those corners are bisected, this side is equal to this side by proposition 5. And we can apply the same reasoning to this triangle here, DEC, and we find that this angle is equal to this angle, and by proposition 5, this side is equal to this side. But we've just divided this whole triangle into 2 equal and smaller isosceles triangles, which proves that one of them is half of the other one, right? So making the triangles DEA and CED, that's what I just did. Isosceles triangles on equal bases. They're on equal bases because these sides are equal to each other because they're just the sides of the square with equal angles about the base. So the angles there are all equal to each other as well. So that means, of course, that not only is this isosceles triangle equal to this isosceles triangle, based on that information, but all the other triangles are also equal, right? All of these little green triangles here are equal to each other by the same reasoning. Now, I didn't go through the tedious exercise of repeating the proof for every single triangle. I've just said, like Euclid does, well, this reasoning is sound, and if we apply it over and over again, we will find that the rest is true, but I'm leaving it up to the reader to actually work that out for himself. Because it should be pretty evident that just by repeating that argument that we can establish that all these four triangles are equal. Okay, so next we say, but because each of these triangles are equal, their corresponding angles are also equal. Well, we know that the angles in the corner are equal, that's pretty obvious, but what about this angle here? Right, these angles here about E are also all equal. Therefore, angle AED, which is this one, here, angle AED is equal to DEC, right? As the triangles are equal, because each one is a right angle is what we discover, right? Because these two angles are equal, they are set up on a straight line, and whenever that happens, you have a right angle by definition 10. And because the vertical angles are equal, right? So we know this is a right angle, we know this is a right angle, but the vertical angles across from them, so the vertical angle here is the angle on this side, this also has to be a right angle because it's the vertical angle corresponding to this one. Similarly, this angle, the vertical angle is here, so these two angles have to be equal as well. But these angles on this side are right angles. Therefore, of course, the angles on the other two sides are also right angles as well. And so after establishing that, we can conclude that because that's true, and we have four right angles here, that AC is therefore perpendicular to BD, and again we know this by definition 10. And that's all there is to it. So I hope that that wasn't too difficult. If you did this a different way, that's okay. There's more than one correct way to do this. For instance, one pretty obvious variation is rather than using 1,4 to prove that these two triangles are equal, ACB and ACD are equal, you can actually prove this using proposition 1,8. That's not difficult because we know that this side is equal to this side, and we know that this side is equal to this side, and all those sides are equal. That's the first thing that we said. And so the only other side we have really to talk about is side here, the side which divides those triangles, but that's equal to itself. And so we have side, side, side equal to side, side, side. And so we can establish the equality there, not with proposition 4, but with proposition 8. So there's more than one right way to do this. But I hope that your proof followed something of this argument. And if you had a dramatically different proof, it doesn't necessarily mean that it's wrong, but it does mean that you'll want to go back and look at it very carefully to make sure that you haven't overlooked something or that you haven't made unwarranted assumptions. It's very easy to assume that something has been proven when it really hasn't been, right? And you've simply introduced assumptions, for instance, thinking that two things are equal without actually going to the trouble of proving it. And you can tell that I've been very careful to prove the equality of everything. I haven't assumed that things were equal simply because they seemed equal or because it seemed intuitive. I actually tried to back that up with real evidence by appealing to the definitions or to the postulates or to individual propositions. So I hope that that makes sense. And that's how we do problem D. Next, let's take a look at problem E, which I hope was a little bit easier, but in the event that it wasn't, we'll go through it again just to make sure that it makes good sense. So again, there's more than one right way to do this, but we're going to simply do this rather quickly. And so we need to construct First, an equilateral triangle. That's the first thing we need to do. And I'll just do that really quickly like so. And then we'll walk through our proof. So here's our equilateral triangle, and we want to prove that it is impossible to construct an equilateral triangle in which one or more of the angles are right angles. So the best way to do this is really to use a reductio proof. And so the way that we would do this is we'd say, okay, we have our triangle. I'm not going to write out the proof. I'm just going to do it verbally and hope that you'll catch what it is that I'm doing. I will try to be clear. So for the reductio proof here, we're going to assume that one of these angles is a right angle. All right, we're going to assume that the angle at B is a right angle. So we're going to say this is an isosceles triangle, which means that all the sides are equal. That's the given, right? That's the thing that we know for sure. All sides are equal. And we're going to assume that this is a right angle. Now, how do we go about proving that this is an impossible situation? Well, there are a couple ways of doing it, but here's one that occurs to me immediately. The first thing we might do is we'll say, okay, well look, because these sides are equal, that means that the angles at the base also have to be equal by proposition 5. Because this is also, we might consider this something like an isosceles triangle. Even though it's an equilateral triangle, it has two equal sides, and we know that equal sides subtend equal angles. And so that means that this side must also be a right angle if that's true. But that also means because this side is equal as well, we have 3 right angles here. And the problem that this creates is if we extend one of the sides, because we know that a straight line set up on another straight line, if it makes a right angle, the other angle must also be right. We know this, right? Okay, so that means that's a right angle as well. But by proposition 16, the exterior angle is greater than either of the interior and opposite angles, which again, this is impossible because this side is actually going to be equal to each of the interior and opposite angles, which is an impossible case, right? Proposition 16 clearly says this can't happen. Again, using the reductio ad absurdum method, which I hope you can see is a very powerful way of proving these kinds of absurd cases, or I should say proving things which are sort of intuitively true but are difficult to prove any other way. It's hard to come up with a positive proof. It's much easier to just assume, to go along with it and say, okay, let's just assume that this really is possible. So we draw in the right angle and say, no, what are the implications? That if this is a right angle, what does that imply? Right? And we found it implies all the angles are right angles, but then we violate proposition 16 there, which creates, of course, a very serious problem. So by all that reasoning, we can say with certainty that it's impossible for any of the angles in an equilateral triangle to be a right angle. So the last thing we're going to do today is work through construction F. Now, I hope that you didn't find it difficult, but it is easy to get disoriented when doing these kinds of problems, so I thought it'd be helpful to walk through how to do it. So construction F has got two parts. The first part is to draw a parallelogram by first drawing a triangle. So we'll just draw a triangle somewhat at random here. So there's our triangle. And we're going to draw a copy of this triangle beside the original triangle so that the two triangles have a common side. And I hope that this language was not too difficult. But the way that I like to think about this is really by imagining that these sides are color-coded, or even by actually going to the trouble of color-coding them, because that can make things much clearer. So this is going to be our red side. And then I'll label one other side. Okay, so now we have two sides color-coded. And this is going to be helpful because one of the things I like to do is I like to imagine how my sides are going to fall. So I'm going to copy this triangle about this side here. And so this means that the sides are going to fall opposite this side. So this means that the red side is going to fall somewhere over here, and the green side is going to fall somewhere down here. So you have to imagine the sides being sort of transposed. And sometimes it's actually helpful to draw in something like this lightly in pencil to give yourself some kind of guidelines for how to do this. So first I'm going to copy the green side with my compass there like so. And of course, because it's going to fall opposite down here, the only place I can really put it is there. I don't know where else this other point is going to be, so I have to put it there. Next, I'm going to copy the red side And we'll do this in the same way. So I've got my red side there. Now, I can't, obviously it doesn't make any sense to put it there because it needs to fall opposite. And I can put it here because it's going to fall down this way. And when I do that, now I have a point where both of these join up. And if I connect these lines, we find that I've copied this triangle about itself. So this is the common side, and I've copied the triangle around it. It's not really a mirror image, because if it were, then the red side would be down here, and this is the thing that makes it a little bit confusing, sort of like an inverted mirror image, which is why I like to imagine simply translating one side across to the other side. But this is how you can do that. So once more, we'll draw a triangle. Here's my random triangle. And I'm actually going to go ahead and color code these sides again as well, because I think that that is a helpful practice. And I'm actually going to copy it around that side this time. So here we have this. I'm going to copy it around the black side. And let's see what we've got. So the red side, let's copy the red side first. Now remember, we can't place the red side here. The circle here isn't going to help us. It's going to go opposite itself. So it's going to fall down here instead, which means the circle has to have the center there. Next, the green side. So we're going to copy this side. And again, we don't want to place the circle there because that's not going to help us out. The green side doesn't fall here. It actually falls opposite itself. So the green side is going to fall down here. So we place the center there. And now all we have to do is join these sides. And you can see how this is the green side there, and how this then is the red side there. And again, we've constructed a parallelogram. Now, you don't have to prove that this is a parallelogram. That was never something I wanted you to worry about. I just wanted it to look like a parallelogram, because we'll get into parallelograms here soon, but it's very important that you know how to draw them. And that's all that there is to it. So I hope that that was helpful. And if you need to, of course, you can go back and rewatch any of these sections. But otherwise, work hard, and we'll pick up where we left off here after cycle 9.